Okay, so welcome to class. We got more people here today, so this is good. Let me just talk about a few administrative tasks here. I have changed the due date for the second project to this coming Saturday, and there is a quiz also due on Saturday. So those two things, I will be posting the next project tomorrow probably, which will be due the following Saturday. I'm going to try and follow that same routine. Post it on Wednesday, it'll be due on Saturday, unless the projects start getting bigger, so we might give them more time then. But
post them on Wednesday and be due a week and a half?
A week and a half, yeah. And I'm going to start having work days for anyone who wants to come and work on stuff. So there will be fewer lectures, more work days. Let's see here, what else we got? So today we actually don't have lecture slides, we have lecture notes. Mainly because I had to figure this stuff out myself, but it's very important.
Oh, I read about this.
Open Sesame. Why are you not opening?
It opens in like the Windows thing. Yeah, there it is.
There we go. Now my question is, can I draw on this? Doesn't look like I can. Why don't they have Adobe? Ooh, what's that?
You just have to specify it to open in Adobe.
Okay, let's do it this way then. Open with... Okay. Here we go. Can I draw on this? Maybe. Highlight text. Add a sticky note. Don't want to add a sticky note. What else we got? What other fun buttons do we have? Whoa.
Comment?
That'd be more typing. I just want to write on the thing.
Go inside, maybe?
Nope.
What do you normally do it in?
I've never done this with a PDF before, so.
What do you normally do it with, though?
PowerPoint. PowerPoint comes with a tool that does that.
Can you open a PDF in PowerPoint?
I think you can. Does it have OneNote on it?
Yeah,
Yes, it does.
Open the PDF in OneNote.
I don't want to connect to the cloud.
Just say...
Just say X.
Yep.
Ah.
That works.
Okay, let's see here. Can I... Downloads. Nope.
All files. Oh. Did
Insert. Can we insert file?
Oh.
Attachment or file printout?
Well, I think attachment's just going to put a link. Oh, there you go. This is fun.
Sorry. Thought this would be easier. Okay, we're going to do this instead. We want the pen software. Opens up this huge thingamajig.
Can you put a file in there? Go to open file. Oh, that works too.
Background image, import images.
Up, left. Yeah.
It wants a whiteboard file.
Oh, it can only open with, oh, that's,
Yeah. That's okay. We'll just switch back and forth.
can you drag it in there?
No.
Okay.
So we're just gonna...
Man, that's
I know, it's ridiculous, huh?
silly.
I'm sure there's a way to do
What
it.
else can
But...
you open it with? Sorry. We don't have to do this. Acrobat should be able to, you should be able to write in that.
Ooh. What do we got here? Lots of fun things.
Go to tools.
No.
I don't see it.
That is crazy.
That is weird.
I thought Acrobat did like everything.
Yeah, I know, right?
Comment? What about comment?
Annotations.
Drawing markups.
Yeah. Found it. Okay. All right, I'm going to have to tell everyone to skip ahead. Alrighty.
Go back in time.
So, today we're talking about how we measure how good our parallel performance is. Okay, and this is scalability. Most of us have probably heard of this. But it's important because it helps you understand kind of where your weak points are, how good your program is. There are lots of ways of measuring this. The two most common is what they call strong scaling and weak scaling. And we're just going to be talking about the simplest possible models. This is all given in section 5.3 in the book. However, the book tends to be really dense and difficult to understand, so I tried to pull out the relevant parts, understand it myself, and I wrote this document up while I was doing that. So, if we have a program, so let's draw a little program here. Here's our program. Okay, and our happy little program. Okay.
Okay, Bob Ross.
You put some little trees next to it.
Yeah,
Little clouds.
we can put some fluffy clouds, huh? Maybe the sun. Okay. Can I change the color? Probably not.
I think you can. I don't know how, but
Nope. Ooh.
tool default properties.
Okay. Anyway, we're gonna have a serial portion. Ooh, that's not what I wanted.
I'm
Oh,
pretty sure you can just draw like on the desktop.
yeah.
you
Well,
should
I
be
don't know
able to
how to
draw.
do that. Why did it do that? That's annoying. Stop it. Escape. Okay. Undo that. Okay. So we're going to have let's say this is the serial portion, and maybe we have a parallel portion. Okay, and then we finish up with a serial portion. So maybe this is reading inputs here. This is doing the calculations here. And then this is writing everything out to a file. Okay. And so we are going to say this program does a certain amount of work. It has a serial portion, the parallel portion, and you add those together, you get 1. Okay, so we're going to say the amount of work we need to do is 1. And if we run this program with one processor, then the time it takes, we're going to say TS is equal to 1. We're going to say that amount of time is 1. So the performance of the code, of a given code, can be defined as the amount of work done over the time it took to do it. And so we have, or I guess in the physics analogy, that'd be power, right? Work over time. So we're going to call this performance. In this case, that performance, again, is just 1. And then, so when we're talking about a parallel run, we can determine the overall speed up of the code, S, is found by taking the parallel performance and dividing it by the serial performance. Okay, and then the very last thing we're going to need to know is what they call parallel efficiency. So if we take the performance on n processors and divide that by n times the performance of one processor, that also happens to be equal to the speed up divided by the number of processors. So that's a little shortcut that you're going to end up needing later on. So basically what this says is if we have one processor and we use, when we're solving this, dumb thing.
So 1's the holy grail. The efficiency of 1.
Yes, efficiency of 1 would be the holy grail. So if we have this one processor and we use it to its full capacity, so we use the whole thing, since I can't draw inside the square. But then if we have 2 processors, maybe 3 processors, what if we only use them half full? We're not, and so that would lower our efficiency. If we use them to a full capacity, that would be an efficiency of 1. Okay, so any questions on the basics there? Make sense? Good. So now we're going to talk about strong scaling. It's a fairly simple idea. If we have one processor that does some work, then 2 processors should do the same amount of work in half the time. So anybody taking any business classes? No? None? There's the law of diminishing returns. If you have X amount of work to do, how many people, if you hire 10 people to make 10 widgets, is that really efficient? You get that law of diminishing returns. And we get the same thing going on here. But if we look at the time required to run the program, in this case, so we have this, time required to run the program in parallel, then we have our serial portion. That doesn't change. Well, at least we hope it doesn't change. If it does, we've got bigger problems. Okay, so that's an assumption in this derivation, is that S never changes with N. And then our parallel portion, that time gets divided by N. Okay, and then you can do some math and find out that the performance of the code is the amount of work, which is S plus P, remember, divided by the time it took in parallel. And we end up with this formulation here. And then speed up of the code is the parallel performance over the serial performance. And the serial performance, again, is just 1. So we get the same result there. So this is known as Amdahl's law. Yes. And I actually came across some history on this. When Amdahl came up with this, all the people that thought parallel processing was stupid loved this. Okay, because if you look, as n goes to infinity, here, what happens to that term? That goes to 0, and we're left with 1 over s. So the amount of speed up that we can get is limited by how much serial processing is possible, which makes sense. If you come back up to our picture, as n gets bigger, this portion here shrinks, essentially. And we're just left with the serial portion of our code. So the speed up reaches a maximum of s equals 1 over s. Big S equals 1 over little s. So thus, if we have a strong scaling scenario, it's critical that we minimize the serial portion in order to improve our scalability. Because let's see here, if we had a plot of speed up over number of processors, in a perfect world, I don't know, it's not going to let me draw on here. We'll draw it backwards. Haha, I tricked you. We would get this. For every processor we add, we get that much increase in speed up. But because of this 1 over s threshold, in reality, we get something that looks like that. And it all depends on s in this case. And so then if we compute the parallel efficiency here, as n goes to 0, as n goes to infinity, this whole term goes to 0. Our parallel efficiency just dies. We're not utilizing our processors as much as we could. And so that's strong scaling. That's the most intuitive one. So the next one we have is called weak scaling. So weak scaling is used to determine how well the program operates when the amount of work is increased as the amount of processors increases. So again, the business analogy, if you hire 10 guys, that means you can do 10 times as much work, not do the same amount of work in 10 times less time, because we all know that doesn't really work. Everyone gets in the way of each other. So instead, we give them all a cubicle and we give them all a completely different job, and we keep stacking cubicles up and we get Google. Or Microsoft. So this one's a little harder. This is what took me a long time. It's not as intuitive to write down in equation form, because if you look at your serial program, or your program running in serial, okay, n equals 1, then it's going to be doing s plus p amount of work. Okay? And we find the serial performance equation in this particular case is equation 3, all the way up here. Okay, so the serial performance is equal to 1, because we haven't changed the amount of work we're doing. But now let's say we want to use n processors, and so we're going to increase the amount of work we have to do proportionally. And so we take our parallel portion and we multiply that by the amount we're going to be using.
Should 10 and 11 be switched?
No. This is the confusing part. Okay? So, in theory, our serial performance... Our serial performance is equal to 1. But now let's say we're going to use n processors, and so we increase the amount of work we're going to be doing proportionally. All right, so we see that here. But then let's run it with only one processor. So we're going to do a lot more work with one processor, and that's what this equation here is showing. And then if we run the same amount of work with n processors, then the time it takes is s plus p. Okay. Essentially, what we're saying is we can do twice the amount of work in the same amount of time as half the amount of work. I feel like Doctor Who up here, timey-wimey, wibbly-wobbly. Okay, so anyway, that's the part that took me a long time to figure out, because the book is dense. We'll just say that. So then we can evaluate the performance. So we take the amount of work we're doing, which is this much, and we divide it by the time it takes, which is this much. And then our applications, so that's our performance equation, and then our speed up is the parallel performance over the serial performance. However, the serial performance is based off of this right here, not this,
So serial performance is always 1.
basically. Yeah. Anyway, so if we do that, we get a application speed up of s plus 1 minus s times n. So this is a linear function of n with a slope determined by s. So if we had s and n, a perfect speed up line would be something that. That would be a perfect speed up line. And then, but instead what we're going to get is a line that looks something like that. Because the S moves that line over. And so if we want to increase our scalability, all we have to do is decrease S, which moves our speed up line like that. The parallel efficiency becomes this equation here. And notice as n goes to infinity, it just equals P. So that's the parallel efficiency. So basically, the smaller your serial fraction of your code is, then the more efficient you can run it in a weak scaling scenario. And so some examples, let's say I saw some really interesting examples. So a strong scaling scenario. Let's say you want to do a search through a text file for a word. Are you going to write more text just so you can use more processors? No. So that would be a strong scaling scenario. The amount of work doesn't change. And so as you add more processors, you kind of run into this bump or threshold of how fast you can actually get that to go. Whereas a CFD simulation, hey, our computers are bigger. Let's run a bigger problem. Okay, so CFD is very much a weak scaling situation.
So is weak scaling kind of, if you have a really minuscule serial amount, like your processing chunk is just orders of magnitude bigger than your serial, it's kind of looking at how good it is at communicating with itself kind of a bit, and the lag between talking to processors a bit.
Yeah, I'm going to get to that. Because so far, my simple little program happy model here assumes that the parallel portion is perfectly parallel. Okay. However, in the parallel portion, we have synchronization points, we have barriers, we have communication, we have all these things that make it not perfectly parallel. Exactly. So this is a very simple model, and the book goes into a lot more detail on how you account for things like that and develops much bigger models. And something I didn't put in the PDF here. If this equation 8, is Amdahl's law, then equation 13 here is called Gustafson's law. Just so everyone knows. Now, again, up until this point, we've been assuming that we've been measuring the runtime of the entire program. Okay? So, and if instead we measure just the perfectly parallel portion, so we measure the middle portion all by itself, then how much speed up do we get? Assuming there's nothing funky going on in here and this is all perfectly parallel, what's our speed up going to be? Right, it'll be perfect. And so what we've done now is we've changed our definition of work. By measuring only the parallel portion instead of the whole program, we've changed the definition of what counts as working. Okay, and this is how we can abuse these metrics to make it look like we're really good and really cool.
Tell me more about doing
I like where this is going.
By changing the definition of what counted as work, we have greatly improved our results. And the book goes into more detail, but the important thing to note here is this bit here. When reporting scalability results, it is necessary to very clearly demarcate and report what part of the code was measured and reported as work. Okay, if you're reading a paper and they just say, we have a parallel efficiency of 0.95%, and then they never say how they got that result, it's suspicious. Okay. Another thing, it is also necessary to report the hardware specifications because the serial portion is dependent on the hardware used. If your hardware is fast and it can do the serial portion fast, that in essence makes it smaller. And so your scalability depends on your hardware. Figure 5.9 in the textbook, which I left at home, shows scalability reported on 2 separate architectures. And I'm actually going to show you an example of this. And then one more cool thing, another useful function of Amdahl's law is that it can give an approximate idea of do we parallelize or do we optimize the serial portion or the parallel portion. And so the textbook derives this following formula, which says that if you are trying to use n processors, which is greater than this, then you should optimize the serial portion. So if our S value is 0.1, then that would be n is greater than 9. So if you were yes.
So up until this point, you've just been calling S and P our work. How would you quantify that in a practical situation?
So just percentages of
Yeah,
the
they're
program.
Right, so they're just percentages of the program. This part of the program is run in serial. This part of the program is run in
So
parallel.
you just measure the total time it takes to run it, and then
Yeah, by percentage you mean runtime, correct?
Yes.
So that one's 10% of the current time if you're running just on one code.
okay.
If the,
Yeah. So time
one
is
processor.
the measure you would use.
Yeah. So anyway, so this is kind of good to know, but in general, you should always focus your efforts on decreasing S as much as possible. Okay, so synchronization points, this would be things like barriers, communication. These things get in the way. A huge one is file I/O, input-output. That will slow your code down like nothing else. And I'm going to give you a little demonstration of that. And then, so things like that will slow your code down a lot more than a load imbalance in the parallel portion. I'm going to talk about that a little bit too. So basically, make sure your code is running fast, parallelize your code. Make sure it's running fast first, and then worry about the parallel portion. Okay. Alrighty. So that's my lecture for today on scalability. And this is posted on Canvas. However, it does not have happy program here, so sorry, you'll have to draw your own. Alrighty, let's just get out of this thing. Okay, so last night I went ahead and did the next project, which was to parallelize the Jacobi method using OpenMP. Oh, don't do that to me. And I am not going to show you my code.
Why not?
You can show it to me now. I'm auditing.
You're auditing the class. I'll show it to you later. Okay, and then we run it. And it goes ahead and does its thing here.
That was boring.
Where are all the errors, man?
Yeah.
Okay,
What's the fun in that?
so I ran this on my lab computer. And what I have here is the speed up of the code. So at 1, of course, we have a speed up of 1. That's kind of boring. But you see with 2, it's pretty good. With 3, it's pretty good. 4, it's definitely starting to drop off. We're seeing that asymptotic line starting to show up. But then, once we hit 5, something bad happens. Do you know what that bad thing is?
Well, it has to split the grid up a different way once it gets to 5.
No, the bad thing is hyperthreading.
Oh.
I have a 4-core machine. And it has hyperthreading, so it thinks it has 8. And you can see that really doesn't work very well. Hyperthreading is a bad thing for us. And so there's that.
It looks like off the line 8 would be about the same as 5 if you truly had 5 cores.
However, then we run into another problem. I have 8 cores on my machine. I still have an operating system running. I have a text editor running. I have my Pandora station running. Have you seen how much memory Pandora takes up? It eats up your RAM like crazy. So if I used 8, it would freeze my entire computer.
Right. But assuming you had, another 4 cores on the side, 8 hyperthread would be about the same as 5 true cores.
Yeah. So obviously it makes no sense to use hyperthreading, but you can see from this line, if I use just 1 through 4, you could actually estimate the serial fraction of the code. Alrighty, so there's that. Now I ran the exact same code on King's Peak. Using one of their systems. All right, so this was a 16-core node. I just asked for a random node. And, I just barely ran this. And I actually had to adjust the size of my mesh. I want to show you something interesting here. First off, we can kind of see, it's being confused. This is not this hard, King's Peak. Apparently it's very difficult. Okay, there we go. It figured it out. Notice we actually get, when we have 2 processors, it goes above ideal.
That makes no sense.
This is what they call super linear convergence because it goes above linear. Any ideas why this would happen?
This was just the Jacobi iteration?
Yeah, this is just Jacobi. It has to do with caches. With 2 cores, you have 2 caches.
They share the same L1 or L2?
No. Every core always has its own L1. Sometimes they have the same or their own L2, which is much bigger. A lot of times they share L3. Okay, but the thing is that with 2 caches, there's now enough space to store more of the memory in the cache, so it can actually operate on it faster than with just 1. With 1, it's a memory-bound code. With 2, it's a cache-bound code. Does that make sense? Because there's more cache available.
And why does it drop below again at 3?
So at 3 is actually perfect,
Okay.
almost.
L3 cache is only shared between 2, right?
It depends. I don't even know what hardware I was using.
I'm guessing.
So,
This has nothing to do with shared cache. This is all about just, you increase the amount of cache with
right,
2, and therefore everything fit in your cache memory.
right.
Why would it then not do the same thing for 3 cores?
Well, now it's quite possible we're starting to run into memory bus issues where there's more memory traffic than can be handled.
Between the cores.
Right. And so at 4, you still see this is really good. A lot better than my computer. The serial fraction on this is much less. 5 isn't so good. 6, 7, okay, and it's starting to, we're kind of following this line here. It's starting to really kind of asymptote. It's kind of wavering around the asymptote there. And my code thought that there were 32 cores because of hyperthreading. And so I had to tell it to stop doing that. But, so you can see there's a big difference between my machine and this machine. This machine's a lot better than mine is.
So basically hyperthreading is largely for marketing, so you can say you have an 8-core machine.
Basically.
What are cases that hyperthreading would actually help?
Hyperthreading is useful for small things,
Small things.
operating system type stuff.
So why is there jumps along the way?
I have no idea.
Oh, okay.
What's up with that big, like at 5, how it kind of flatlines to 6?
Again, I don't know. A lot of it has to do with the actual hardware. And I don't know how that hardware was set up, but let me just draw you a potential example. So if we have a 16-core node, and these nodes could be arranged like this. I have a pen.
Just gonna wonder that.
Thank you. I have a pen.
I mean, that was impressive. Don't get me wrong.
Let's just do this. That's easy enough. Okay, so this node that I'm drawing here, I don't know, has 4 sockets and has 4 cores on each socket. Okay, so it very well could be that is there any other colors?
No.
In game.
You're limited to 3.
We don't know how these were arranged. So when I ran one processor, maybe it ran that one. When I ran 2 processors, maybe it ran that one. And it very well could be that each socket has its own memory bus. And so it went 1, 2, 3, and 4. But then when we did 5, now these 2 are fighting over space. Okay? And then we have 6, 7, 8, kind of in a round robin fashion here. It all depends on the hardware. How the hardware is set up, what it can handle, which is why you have to report scaling results with your hardware. Anyway, so I thought that was pretty interesting. I haven't done a weak study because weak studies are harder to set up correctly. But the next project is going to be doing a strong and weak scaling study of this. Alrighty, so anyway, that's all I had for you guys today. Any questions, comments, accusations?
I'm sure I could think of something if you gave me long enough.
I would love to see you graph with the strand code. Just